As I told you about the electrolyte, the phenomena of electrolysis, you know everything now, right? We know that electrolyte are of two types, strong and weak electrolyte, right? And you also know what is actually degree of dissociation, right? So we will be just taking into the consideration Ostwald dilution law now, which will just indicates that the degree of dissociation depend upon which factor, right? So before I state the, you can say a statement for this law, I just want to explain you mathematically so that we can derive the mathematical expression, and then you can be well versed with what actually the Ostwald dilution law wants to state, right? So for this, what I am doing is, so first of all you should know that why we are doing this Ostwald dilution law, right? It is just to indicate the degree of ionization for weak electrolytes, right? So what is it actually? So I'm just taking an example for you. Suppose I have an electrolyte AB, right? So it is present in aqueous state. So I know that electrolyte is a substance which has the ability to get dissociated into the ions, right? So this is how it gets dissociated into ions. And as we know, in case of weak electrolyte, there are ionized, the molecules are also there, and there are unionized molecule as well. That means the ions are in equilibrium with the unionized molecule. You know that we did in the electrolysis, that how it happens, right? So I am just considering an example. Suppose I am taking an example of acetic acid. I think you are familiar with the acetic acid. It is just a vinegar that is used in a kitchen, right? So the formula for acetic acid is CH3COOH. It is a weak electrolyte. That means it gets dissociated into acetate ion and hydrogen ion, but it do not get completely dissociated. So that means there exists an equilibrium between the ionized, you can say the ions and the unionized molecules. So this I am indicating by, you know, that this is the reversible sign. That means they can also form this, and even they can reunite to form the unionized molecule, right? So now we know from the law of chemical equilibrium that I can write the equilibrium expression for it, right? So similarly I am doing it here for this equation. So equilibrium expression is that K is equal to the concentration of product, that is acetate ion, right, and divided by the reactant, concentration of reactant, right. So this is the equilibrium expression, right, that is CH3CO negative H positive divided by the concentration of the reactant, that is CH3COH, right. So this is the equilibrium constant expression that I have written for this equation, right. Now what I am doing is I am just considering that there is a concentration. I am just going to take a certain value, a certain variable used for the concentration, right. So what I am doing is, like for this reaction I have, suppose we know there is an equilibrium between this and this, right. Suppose if the initial concentration of acetic acid is initial concentration when it is not dissociated, right. So initial concentration taken into the consideration was C. So the acetate ion was the initial concentration of acetate ion was 0, and for the hydrogen ion also is 0, right. So but at equilibrium, when it gets dissociated, what we get to see, we see that the concentration left for acetic acid is C1 minus alpha. You know that what the alpha is. It is the degree of dissociation, right. So suppose at equilibrium the concentration we are left, or you can say the concentration which we get to see for acetic acid is C1 minus alpha, and for acetate ion it is C alpha and C alpha, right. So now I am just putting this value of the concentration in this equation, right, because this indicates, this bracket indicates the concentration, and we know that the concentration in equilibrium is this. So I am just putting this value into this equation. So this becomes C acetate ion is C alpha, right, H ion is again C alpha, and acetic acid is C1 minus alpha, right. So this just I have put the expression, you can say the value in the concentration expression, right. So now I am solving it. Then what do I get after it? So that means K is equal to C square alpha square, you can see C square alpha square divided by C1 minus alpha. Here C cancels out, so we are left with K is equal to C alpha 1 minus alpha, right? So now if I consider it as a weak electrolyte, we know that in case of weak electrolyte, the degree of dissociation is too small. So that means if it is a weak electrolyte, like I took an example of weak electrolyte, you know that. So if it is a weak electrolyte, so in this case, alpha can be neglected because degree of dissociation is too small. So I am just removing the, or I am not taking it, I am just neglecting the alpha present in the denominator. So after removing, what I get is K is equal to C alpha upon 1. Sorry, it was alpha square. So it is K is equal to C alpha square upon 1. So that means degree of dissociation for weak electrolyte comes out to be K upon C. That means the square root of K upon C, right? So this indicates the mathematical expression for Ostwald dilution law, right? So what information do you get from this equation? That means, what do you think that Ostwald dilution law wanted to state by giving this mathematical expression? You are right. It indicates that the degree of dissociation is inversely proportional to the square root of the concentration of solute. As you can see, we have got the C in the denominator, and there is a square root as well as present, and K is a constant, right? So this Ostwald dilution law states that the degree of dissociation is inversely proportional to the square root of the concentration. We can have this law in other term also, right? So just look at the board, what I am doing. So see, this is a concentration. Suppose concentration of solute present is moles per liter, right? So moles per liter, M indicates moles and V indicate the per liter indicates the volume, right? So I have the concentration is equal to M upon V, right? So if I consider 1 mole, if I take M as 1 mole, so what can I write? I can write that C is equal to 1 upon V, right? So I can just put the value of C in this case. So then what it will just resolve to form? If I put this value 1 upon V, the value of C into this equation, what do I get? I will get alpha is equal to root K into V. So this is the second statement of the Ostwald dilution law in terms of volume, right? So we can, this law states that the degree of dissociation is inversely proportional to the concentration of solute, or it can be defined as the degree of dissociation is directly proportional to the square root of the volume of 1 mole of solute present in a solution, right? So by either way you can explain the Ostwald dilution law. I think it's clear. Once again, just look at the board. This law is just stated for the sake that how the weak electrolyte gets dissociated, or we can just, it can just tell the extent of dissociation or the extent of ions which are formed in case of weak electrolyte, right? So what we are doing, I am taking into consideration any weak electrolyte, just take it on the left side, put reversible sign and make the ions, right? You know that in case of weak electrolyte we have the reversible process. So this is what I have shown here, right? Then what I did, I wrote an equilibrium constant expression for it. We know that the concentration of product divided by concentration of reactant. This is what I have done in this case. Then what I did, I took the concentration value as C initial and 0, 0, and at equilibrium C1 minus alpha and C alpha, C alpha. I just substituted this value in this case and just solved the equation, and what do I get at last? Alpha is inversely proportional to the square root of the concentration, and by putting the value of C we can just transform this law in terms of volume. That is, the alpha, that is the degree of dissociation, is directly proportional to the square root of the volume of the the solute present, volume of 1 molar concentration of solute present in the solution. So this is actually the Ostwald dilution law.